interview. So I have to I had to join my I to join through my mobile. So sorry for the delay from my side too. Anyway, so before I start my actual lecture, usually I used to mention where do I come from because probably you guys should know what CECRI is all about. On a very lighter side, I went for graduate in a place like Karachi. Probably you guys know this is a very small town. And the barber asked me, sir, in a very typical Tamil slang, where do you work? I said I work in a place called the city. So what is the immediate response from the barber? He asked me a question on a very spontaneous note that do you guys make atom bomb? I was I was very surprised to hear such a question from a barber. So what I decided from that moment onwards, wherever I go and whatever the talk I give, the first slide would be where do I come from. Okay. In fact, I come from an institute called CECRI, which is Central Electrochemical Research Institute. It is one of the constituent laboratories of CSIR. We do have three different subunits. The headquarters is located at Karaikudi. We do have subunits like in Chennai, Tuticorin, and Mandapam. We are roughly about 100 employees, out of which one-third are scientists. Even now in India, this is the one and only research institute devoted completely to the field of electrochemical science and technology. Okay, I repeat the sentence again. CECRI is the one and only research institute in India completely to the field of electrochemical science and technology. In fact, we do work from looking at fundamental aspects of electron transfer reaction across the interface, electrode-electrolyte interface, to material design for target applications, and we do fabricate, prototype instruments, device for many functional applications. Right. Apart from this, we do have good analytical facilities. One can carry out any kind of electrochemical science and technology research with that facility.
Sir Ganesh, sir. Sir Ganesh, sir.
Please, sir. Yeah.
Yes, sir. Your voice is little breaking. Is it possible to make it little clear?
Okay. It's breaking.
Yeah, it's a network. I think the network is a little less. I think that is the problem.
Sorry, sir. Echo
is no problem. I think the network is not so good. I think.
Oh, is it okay? I'm connecting it from BSNL. Maybe I will try. Then we will see where it.
But your institute internet is not yet okay, or?
It does not restore. It's still off only.
Okay.
Am I clear now? Audible or still breaking?
Yes, it's little breaking. So voice is little breaking. So some of the sentences is not so clear to audible. That is the thing.
Oh, is it okay? Oh. Let me see. I just try to bring an angle where I can get more.
Yes, sir.
Yeah. Okay. How else, sir? Is it clear?
Now it is better, sir. Little better.
Little better. Okay. Let me continue. If the internet restores in our institute, I will switch over. Okay. So so apart from this, we do have a unique course which is BTech in Chemical and Electrochemical Engineering. Of course, students after completing 12th, they can take up this BTech course, and most of them are after completing PhD in abroad. Right. If you look at the history behind CECRI, the foundation stone was laid in the year 1948 by then Prime Minister Sri Pandit Jawaharlal Nehru, and it was declared open in the year 1953 by then President Sarvepalli Radhakrishnan. Okay, and of course you can look at the photo that apart from Dr. Sarvepalli Radhakrishnan, we do have a man which is who is standing right next to him is Dr. Bhattacharya, the founder of CSIR. And in between the two, there was person who is speaking in the photo, right? And he is Dr. R. The well-known philanthropist who belongs to this part of the world. You know, because of his city exists now, he has donated 100 acres of land and 15 lakhs of rupees to establish an institute like CECRI. As you can see, we are roughly about 7 decades old, and we do work completely in the area of electrochemical science and technology. Now, interestingly, during the inaugural function, this person was there. I hope you all know who this person is. He was the laureate, Dr. Sir C.V. Raman, right? And during the inaugural function, he posed such a question: what if this laboratory is going to do? Unless otherwise, the workers in this laboratory feel that it is up to them to do their very best. Otherwise, these laboratories will remain as a giant question mark in the sky. Of course, he was a physicist. He was looking at the sky. So during the inaugural function on 14th January 1953, Sir C.V. Raman posed such a question. So you can imagine, it's like you invite somebody to inaugurate a department in your university, let's say, and suddenly that person asks you such a question like, why do you want to start such department when there are, let's say, thousands of departments exist as India? How do you guys feel about it? Now, the same feeling CECRIans had probably during 1950. But I'm sure Raman would have been alive today. He would have been more than happy to see what CECRI has contributed overall to the growth of electrical science and technology in general, and particularly to the growth of India. I can list down many achievements from CECRI, starting from providing corrosion prevention coating to bomb and bridge, and developing ion selective electrodes for specific like pH reduction, chloride ion reduction. Then apart from this, we also developed what is called electrode. So many such developments happened over the period of time. To the latest addition being Make India project of fabricating lithium-ion cells at Chennai. So we have a center which is established very recently to fabricate 100 cells per day. That's the target we have now. Okay. So am I audible or still my voice is breaking? Is it okay? Am I audible? No response. Is it okay? Am I audible or still my voice is being said?
Still it is breaking.
Still it is breaking. Oh, okay. I'm not sure. I have joined from BNL Mobile. Suddenly our institute internet went off. So let's say I'm just here and there so that you get a good signal. Okay. Now, celebrate Science Day in order to commemorate the discovery of Raman. I'm sure you guys should know, the history behind the Raman discovery. Say till now, Raman was the one and only scientist who got Nobel Prize for the work he has done completely in India. Okay, I rephrase my sentence again. Even now, Raman is the one and only scientist who got the Nobel Prize for the work he has done completely in India. Okay. In fact, he got Nobel Prize in the field of physics in 1930 for the discovery of Raman, right? And in order to commemorate that discovery, we will celebrate Science every year on February 28th. Okay. So if you look at the history behind this Nobel, right? I hope you guys know what the Nobel Prize is all about, right? This is the week Nobel Prize will be announced. Nobel Prize Award winners will be announced during this week, second week of October. And December 2nd Saturday, December 10th or 11th, every year, the Nobel Prize award ceremony will happen in a place called Stockholm in Sweden, except the Nobel Prize for Peace. The award ceremony will happen at a place called Oslo in Norway. Why do I talk about Nobel Prize is because though we had many Nobel laureates from India, but Raman was the one and only one who, in the field of science at least, who has worked completely in India. Okay. Now, so this is the quartz spectrograph Raman used to demonstrate the discovery of Raman effect, Raman signal, through a famous lecture in Bangalore on March 16, 1928. Okay. Now, these are the Nobel Prize winners from India. In fact, the Nobel Prize prizes are usually awarded to 6 different fields, starting from chemistry, physics, physiology, or medicine, economics, peace, and literature. Okay. So we do have many Nobel laureates from India, starting from Rabindranath Tagore to Sir C.V. Raman, Harman Khurana, to recent addition being with Banerjee in the field of economics in the year 2019. As you can see, as far as science is concerned, we do have many NRIs who got Nobel Prize, but among them, Raman was the only one who has worked in India in a place called Indian Association of Cultivation of Science in Canada. Now that's about Nobel Prize because I want you guys to know about what this Nobel Prize is all about, so that you can translate this into the field of science and technology. Okay. So as far as I am concerned, basically I am a chemist. I do work in chemistry. And I do take concepts from material science and biology to come up with sensors and catalysts, and I do work on a small prototype device fabrication, mainly in the area of energy and environmental science and for biomedical applications. So, as far as today's talk is concerned, I will try to highlight fundamental concepts behind the electrochemistry as a whole. I will try to explain you why electrochemistry is important in the context of energy, in conversion and storage devices, and I will try to highlight some of the basic principles and theory behind electrochemical techniques that one can use for solving global issues. Okay. Now, if someone asks you what is electrochemistry, so your answer would be yes, it's a branch of chemistry in particular. It deals with study of electron transfer reactions at interface. Okay. So what do I mean by that? Let's say why one has to worry about electron transfer reaction. I ask a series of questions. You guys don't answer. Just think about it. Let's say we all have good food in the night. Okay. And after good dinner, we go to bed to sleep, right? And who asked you to wake up in the morning? Probably you would have kept an alarm or disturbance from our, spouse or kids, friends, mobile phones, etc. Let's say we do get up in the morning, and after a couple of hours or so, you feel very hungry, right? So why do you feel hungry? Let's say you take some good breakfast. After the breakfast, we go to a bus stop to catch a bus to come to university or institute. When you get into bus, when you look at someone, you feel very happy. And when you look at someone else, you feel very much irritated, right? So rather, I would like to say that we express our emotions. Okay. So why all these things happen? That's the question, right? And you guys would generally say that all these things happen because of biochemical reactions which occur in our body. Okay. And I would go one step ahead and say that all these things happen because of electron transfer reactions which occur in our body. Do you get me? All these things happen because of electrochemical reactions which occur in our body. The moment you talk of any biochemical reaction, there could be some molecules which can undergo oxidation and some other would undergo reduction to bring about all these changes what we discussed a while ago, right? So that's why understanding electron transfer reactions becomes very critical. You can even correlate with the human behavior aspect as a whole. Okay. Not just that, So any study which deals with such kind of electron transfer reactions at interface, it could be solid liquid interface, it could be solid gas or liquid gas interface. Okay. So that kind of study is nothing but your electrochemistry. Now, in general, electrochemistry deals with two different kinds of reaction. Okay, two different kinds of reaction. What are those two categories? The first one, in which you can apply the voltage to drive a chemical reaction. And the second one, the voltage is generated because of inbuilt chemical reaction. Okay. Right now we assume that the voltage term. I will try to explain where does it origin from. Okay, a bit later. These are the two different categories what electrochemistry deals with. Let's take an example. What do I mean by voltage is generated because of chemical reaction? Okay, let's say we all have wall clock in our house. Okay, the moment wall clock stops, what do? We simply change the battery, right? And the moment you connect a battery, the clock starts working. Why does it work? Because it provides an voltage because of the inbuilt redox reaction, inbuilt chemical reaction associated with the battery. So that's the kind of reaction what electrochemistry deals with. Okay. The other kind of category is voltage is applied to drive a chemical reaction. What do I mean by that? Let's say probably you guys should have read a recent newspaper saying that water could be used as a fuel to drive vehicle. Can we really use water as a fuel to drive vehicle? Okay. How about thermodynamics of that reaction? I will talk about water splitting probably tomorrow in a very broad way. Right now, you are saying that yes, we can use water as a fuel to drive vehicle, provided you split water into hydrogen oxygen. How do you split? You can apply an voltage about 1.23 volt versus normal hydrogen electrode. If you apply, water could be split into hydrogen and oxygen, so that both could be used as a fuel. So that's the kind of category that comes under the first category of electrochemistry, where one can apply a voltage and drive a chemical reaction. So such kind of redox reaction one can study, and the study which deals with such kind of processes is nothing but electrochemistry. I deliberately put a couple of images from Google. You know, the moment you type electrochemistry, you would get such kind of images, right? You guys know, even you take a fruit like lemon or orange, you can prick the fruit with two conducting rods, and that would establish an electrochemical cell at the interface, and that will get an voltage, right? Now, so in general, electrochemistry could be used to tune delta G. What do I mean by delta G? Right? Delta G is nothing but your Gibbs free energy. As you can see, the equation delta G is equal to minus NP. In this equation, N is number of electrons associated with the process, F is Faraday's constant, and E is nothing but your potential. Now, for a given process, the parameters both N and F are constant. The only variable parameter is E, that is potential. So what does it tell you? By changing the potential, you can basically play with the delta G. You can tune from a non-spontaneous to spontaneous and vice versa reaction. You know, that's where the first category where voltage is applied to drive a chemical reaction. You know, thermodynamically, water splitting reaction is not allowed because you do have a large activation energy barrier. But by applying a potential of about 1.23 volt versus normal hydrogen electrode, you can split water. So that's where applying potential used to tune delta G. Okay. So if we look at electrochemistry as a whole, compared to the chemical concept, where if you want to probably these two graphs you would have read during your probably schools or undergrads, right? For example, a reaction to undergo, the reactant has to cross an energy barrier, which is an activation energy barrier EA, and the moment it crosses, it can undergo a chemical reaction to give you the product. Now, you can reduce the activation energy in a normal chemical reaction by, let's say, using a catalyst or by applying a temperature or by applying pressure, etc. Correct? So that you can reduce the activation energy barrier and the chemical reaction can undergo to give you a product. Now, in case of electrochemistry, apart from these parameters, you also have current and potential to tune such activation energy barrier. Okay, so that's the added advantage we do have in electrochemistry. Now, I keep on mentioning a couple of terms in electrochemistry like current and potential. Now, where do the potential originates from? Okay, let's look at the very fundamental concepts of where does the potential originate from. The moment you dip any conducting rod into an electrolyte, let's say you dip a copper rod into a sodium chloride solution. So this scenario establishes an electrode electrolyte interface, right? A solid liquid interface, where the dipped copper electrode will act as an electrode and sodium chloride solution, let's assume it will act as an electrolyte. The electrode will act as an electronic conductor, okay, and the electrolyte will act as an ionic conductor. The moment you dip an electrode into an electrolyte at solid liquid interface, it establishes a double layer structure, right? It establishes a double layer structure. What do I mean by double layer? There is a separation of layer of charges across the interface. Let's say, let's assume the metal has a positive charge and the corresponding negative charge would come from the electrolyte part. So this separation of layer of charges across the interface establishes a double layer structure. In turn, this gives you a parameter called capacitance, right? C. What's the relationship between capacitance and potential? It is correlated through charge stored at the interface. So C is equal to Q by E. Do you get me? The capacitance C is equal to Q by E, where Q is the charge stored at the interface. In fact, that's the origin of potential in electrochemistry. The potential arises because of the spontaneous formation of double layer at the interface. Now, I will describe a little bit about double layer structure a while ago. Right now, let's assume that is it possible to determine potential of a single interface? The answer to the question is no. We cannot measure potential of a single interface. Rather, what we can measure is the potential difference between two different interfaces. Okay, so how do we understand this concept? I used to tell a story during my classes here at for PhD student. For example, let's say someone is a good cricket player. Okay, let's assume he is a very good batsman. How does one can say that he is a very good batsman? By comparing with a very good batsman like Sachin Tendulkar or Virat Kohli or Dhoni, etc. Correct? So, similarly, in order to measure the potential of a single interface, we need to use another interface. Remember, you can use people like Sachin, Dhoni, or Kohli as a reference, provided they perform consistently, right? A couple of matches they scored 100 and another couple of matches if they out at 0 continuously, then we cannot use them as a reference. Do you get me? You cannot use them as a reference for comparison. So clearly, in order to measure potential of a single interface, we have to use another electrode. Okay. So the moment you dip another electrode into an electrolyte, that establishes another double layer. In turn, it establishes another potential. The moment you take a lead from these two electrodes and connect to a voltmeter, that display a voltage value. So that means you measure the potential difference across the interfaces. In order to measure precise value, we keep one electrode as a reference electrode. That's where we use electrodes like normal hydrogen electrode, saturated calomel electrode, silver electrode, mercury mercurous oxide, or mercury mercurous sulfate electrode, etc. All these things could be used as a reference electrode. Okay. Remember, the potential of normal hydrogen electrode is assumed to be 0 volt. Okay, so even if you want to describe a half cell of a standard hydrogen electrode, which is nothing but a platinum electrode dipped in 1 molar HCl, that interface would also display a potential value. But for our convenience, we assume the potential of normal hydrogen electrode as 0 volt. So based on that, we arrange EMF series, right? We arrange electromotive force series, in which whichever the element that undergo oxidation, we keep positive potential, we keep above the hydrogen electrode, and whatever the element that undergo reduction, we designate them as a negative potential, and we keep those elements below the potential of hydrogen electrode, and that's how we frame the EMF series, right? Now, so when you look at the double layer structure, there are different models have been proposed for this double layer structure. Okay, there are models like Helmholtz-Perrin model, Goy-Chapman model, and Stern model are usually available in the books which describes the double layer structure. But apart from that, there is a fourth model of electrical double layer which was proposed by Bakris and Devanathan. Okay, why I mentioned that fourth model is because the person Devanathan was working at CECRI during 1960s when they proposed the fourth model of electrical double layer. In fact, Bakris was also working here at CECRI. Okay. Now, what do? They basically corrected the capacitance measurement value by including the dielectric constant of the solvent and the dipole moment of the solvent, which essentially arises from the electrolyte component. Okay, so that's how the potential is originated in electrochemistry. Now, normally we do use three different electrodes in electrochemistry. One is working electrode or test electrode. That's where you monitor the electron transfer reaction. The other one is a reference electrode. So you measure the potential difference, the actual potential value of working electrode with respect to reference. So that's where the potential exists between reference and working. And the resultant current will flow between working and counter electrode. Okay, the resultant current will flow between working and counter electrode. Now, normally we do use at least 100 times higher surface area or 100 times higher geometric area of the counter electrode compared to working electrode. That is because to minimize the current value due to counter reaction. Okay, that's the kind of basic concept one should understand. Now, if we look at in general any electron transfer reaction, the following are the steps that will happen at the electrode-electrolyte interface. Let's say you have a redox probe, you have a molecule that can undergo electron transfer reaction dissolved in the electrolyte, and you keep the electrode as a working electrode and you monitor the reaction. The following are the steps through which an electron transfer reaction will occur. The redox probe molecule will diffuse from the bulk to the interface, get adsorbed on the electrode surface, undergoes electron transfer reaction to give you a product. Okay, it can either lose an electron to the electrode and undergoes oxidation, or it can accept an electron from the electrode and undergoes a reduction. So it undergoes an electron transfer reaction to give you a product. The product discharged and diffused back to the bulk of the solution. Okay. So among these processes, whichever process is slower is called the rate determining step. Do you get me? Among these processes of diffusion from the bulk, adsorption, electron transfer reaction, product formation, and the product has to discharge and diffuse back to the bulk of the solution. So among these processes, Whichever process is slower is called a rate determining step. And usually, diffusion of ions from the bulk to the interface is slower. That's why you do observe peak formation in cyclic voltammetry. Okay, I will describe this a bit later. Now, I deliberately put this slide to understand that whatever the electrochemical equipment we use, I do know that the suppliers would give you at a very high price. Okay, but it is easy to fabricate on such kind of potential stat from by ourselves itself. Okay, so probably you would have heard that I'm a chemist basically. When I went for a PhD at RRI Bangalore, my guide asked me to fabricate a potentiostat on a breadboard, which is the image I shown on the right side of the slide. Okay, so I was wondering, why my guide asked me to do a physics experiment, though I am from a chemistry background. Okay, but my guide was, a very good human being. He was smiling and say that Ganesh, simply you do whatever I say, you will understand this at the end of your PhD. So now I realize why he asked me to fabricate a potentiostat, because unless otherwise you do fabricate and understand how the equipment works, it would be very difficult to understand if you face any problem. Okay. So in electrochemistry, what do we do mostly? We do fabricate, we do apply a potential and monitor the current due to electron transfer reaction. Okay. So what we need in terms of electronics is two op-amps, meaning two operational amplifiers based circuits. We can use two ICs, integrated circuits. One is a voltage follower. That is because the working electrode has to feel whatever the potential you apply. So that is a voltage follower. And the other one is current voltage converter. The moment you dip the working electrode into an electrolyte, let's assume if there is an electron transfer reaction, which will provide a change in voltage across the interface, and you pass that voltage through a resistor, you get a current as an output. Okay, so that's why we need current voltage converter. So on a whole, by using these two operational amplifier based circuits, one is an voltage follower and the other one is a current voltage converter. Okay, so by playing with these two ICs, one can fabricate a potentiostat or galvanostat that could be used for understanding electrochemical reaction. I'm sorry, this slide is slightly blurred, but I can able to explain the concept. Okay. Now, by applying a potential to the working electrode, okay, I did not talk about where does the current come from yet. The current essentially originates in electrochemistry because of Le-Chatelier principle. What do I mean by that? How do we understand? Let's say now that we moved from classical blackboard based teaching or conference and a physical present way of presenting to a virtual mode of lecture. Let's say if someone is listening to me in the talk, okay, and while walking across the corridor, suddenly I hit that person. Okay, assume that he doesn't know I come here, I come there to deliver a lecture. So what would be immediate reaction from that person? Immediate reaction would be that person would hit me back. Correct. The moment I hit that person would hit me back. That's the kind of response you would get. Okay. So this could be correlated directly with the electrode-electrolyte interface. That's what Le-Chatelier principle talks about. If a system is at equilibrium, okay, if the system is at equilibrium, if you apply a stress, the equilibrium will shift in such a way that it will nullify the stress. Now, how do I describe an equilibrium? Probably you guys should have read about it. The rate of forward is exactly equal to rate of reverse reaction, and there is no mass change between forward and reverse. Delta M is 0, and in case of electrochemistry, delta I is also 0. There is no current change between forward and reverse reaction. Unless otherwise a system satisfies all these three conditions, you cannot term the system is at equilibrium. Now, why do I have to worry about equilibrium? It's a very tricky question. Like, why do I have to worry about equilibrium? Is because equilibrium is a state where the electrode electrolyte interface exhibits its real characteristic. What do I mean by that? Let's say I tell you a small story so that you can understand this much better. I'm still audible, right? Or my voice is still breaking? Is much better now? Are you guys are listening to me?
Yeah, it is better now. It's okay, no problem.
Okay, sir. Okay, I just want to cross check now and then.
Yeah, yeah, yeah.
You know, people.
It's fine, sir. Please, sir.
Yeah, yeah. Okay. So, why do I have to worry about equilibrium? Is because let's assume someone has got a gold medal during their master's degree. Let's assume, okay, that person goes to the stage and receives the medal, comes to the other end of the stage. Okay. So after receiving the medal, suddenly some of his or her friends go to that person and talk to them. Okay. How many of you guys think that that person would exhibit his or her real characteristic? You know, it would be very difficult to assess because at that moment, the moment that person receives an award or a gold medal, that person should be at excited state. And at that moment, that person will think that he or she is the one and only person in the world who knows the subject very well. You know, that may not be true, but it is okay. That person would be at the excited state. So, at the excited state, he or she will not exhibit her or his real characteristics. On the other hand, on a regular day, when he or she comes to the class, that student may be obedient. He or she may be very friendly, helping to their friends. So they exhibit a real characteristic during equilibrium state. That's why it is very important to understand the system at equilibrium. The same concept could be extrapolated to electrode-electrolyte interface too. Okay, at equilibrium, the system exhibits its real character. That's why, sorry, that's why in electrochemistry we do have techniques that can understand the system, that can understand at equilibrium like potentiometry, and near to equilibrium you can use other kind of techniques, and the other one is far away from equilibrium like voltammetry and pulse techniques, etc. Now, so coming back to lead principle, where, when you apply a stress to the system equilibrium, the equilibrium will shift in such way that it will nullify the stress. In fact, the origin of potential is a kind of disturbance. The scientific term for disturbance is called perturbation. The origin of potential is a kind of perturbation to the system at equilibrium. And in order to get rid of that perturbation, the system responds, and that response is nothing but your current. Okay. So now, when I say you apply a potential and carry out the electron transfer reaction, what exactly happens? What is the fundamental concepts behind the electron transfer reaction at interface could be explained through this images. Okay. Now, let's say normally we use metals or semiconductor as an electrode. So that has a well-defined band energy. The moment you apply a potential, let's say by convention, positive potential, the positive sign is assumed for both potential and current for oxidation process, and the negative sign for potential and current is designated for reduction process. Do you get me? So let's say when you apply a potential, what we do is we shift the energy level on the electrode surface so that, suppose let's say you apply a positive potential. So what we do is we bring down the energy level on the electrode surface so that the species A in the electrolyte loses an electron, undergoes oxidation to give you the product. So that's how the oxidation occurs. So that the species A can donate an electron to the electrode because the electrode level is brought down highest occupied molecular orbital of the species from the electrode. So species can donate an electron. So that's how the oxidation occurs. Similarly, when you apply a potential to the electrode, you can adjust the energy level on the electrode in such a way that you bring above the HOMO of the species so that the LUMO, lowest unoccupied of the species. So the electrode can donate an electron to the species, or in turn, the species can accept an electron, undergoes reduction to give you the product. So that's how, in principle, oxidation and reduction occurs by potential in case of electrochemistry. Now, I will also try to highlight why electrochemistry is such a powerful technique. Okay, let's say the moment you dip any conducting electrode into an electrolyte, I mentioned that there is a spontaneous formation of double layer at the interface. That leads to a parameter called capacitance, and in turn, the potential is originated because of the double layer structure. Now, in case of double layer, the very next layer to the electrode is called the inner Helmholtz plane, and there would be negative charges arises from the electrolyte, and the next to inner Helmholtz plane is called the outer Helmholtz plane. Okay, and beyond which the molecules are in random diffusion, that is called the diffusion layer. Now, why electrochemistry is powerful? Because the typical thickness of the electrode electrolyte interface is of the order of nanometer. Okay, is of the order of nanometer. Even if you apply 100 millivolt, okay, even if you apply 100 millivolt to that interface, the electric field felt at that interface is very, very high. You can calculate the electric field by using the following formula, right? The voltage applied divided by distance of separation. Let's say 100 millivolt within the nanometer level, 100 millivolt divided by 1 nanometer, you would get 100 into 10 power 6 volt per meter. Do you get me? It would be 100 into 10 power 6 volt per meter, which is humongous. Though you apply a very, very small voltage of 100 millivolt, the electrode electrolyte interface will feel as if it is 100 into 10 power 6 volt per meter. That's why many chemical reactions which are not possible through normal chemical method, one can carry out such reaction using electrochemistry, just because the electric field felt at the interface is very, very high. Okay. Okay, so that's the advantage of electrochemistry one can talk about. Now, you guys know that the electrochemistry in fact started with this person, Faraday, who is the man in the discovery of electrolysis, electrodeposition, electroplating, etc. Sorry. So you do know that Faraday's laws of electrolysis, which starts from the first law, which talks about the amount of substance deposited is directly proportional to the quantity of electricity passed, right? And similarly, the second law talks about if you deposit two different metals, the amount of deposited metal is proportional to their corresponding equivalent weight. Okay. Now, so recall the many different processes which I talked about during the course of electron transfer reaction: diffusion of molecule from the bulk to the interface, adsorption of species, electron transfer reaction to give you a product formation, and the desorption and diffusion of product back to the bulk of the solution. Now, the current in electrochemistry arises because of three different modes of mass transfer. Okay, they are migration, diffusion, and convection. Among all these processes, diffusion is the predominant mode of mass transfer, and keep it in mind, all the equations in electrochemistry are derived based on the assumption that diffusion is the predominant mode of mass transfer. So we need to eliminate current contribution from migration and convection. How do we eliminate it? Before that, we can look at what are the definitions of these three different modes of mass transfer. In fact, migration deals with the movement of charged species due to difference in electric field, due to gradient in the electric potential. Okay. Similarly, diffusion arises because of the movement of charged species under the influence of chemical potential. What do I mean by chemical potential? Under the influence of concentration gradient. Okay, so that leads to a process called diffusion. And finally, convection arises because of mechanical disturbances, okay, because of hydrodynamic transport processes. So among these three processes, we need to eliminate migration and convection because diffusion is the predominant mode of mass transfer, and all the equations in electrochemistry are derived based on the assumption that diffusion is the predominant mode of mass transfer. Now, how do we eliminate migration? We can eliminate migration by using what is called the supporting electrolyte. Supporting electrolytes are nothing but species that do not undergo any electron transfer reaction. Okay. For example, we can use species like sodium chloride, sodium fluoride, sodium iodide, or lithium chloride, lithium perchloride, sulfuric acid, HCl, etc. All these things could be used as a supporting electrolyte because those species do not involve in electron transfer reaction. And similarly, one can avoid convection, but by avoiding any kind of mechanical disturbances. Probably you guys would have observed, suppose if you are a PhD student, in your lab, the electrochemical equipment would be kept on a very heavy slab, okay, like a granite slab or a heavy wooden table, etc. That is because to avoid disturbance from mechanical changes, or you need to also avoid the eddy current arises due to vibrational changes. Okay. If you don't have such kind of a heavy slab, you can use what is called a Faraday's cage. Probably you guys would have also seen Faraday's cage. You can keep your entire electrochemical cell into the Faraday's cage and carry out electrochemical study. So by using such kind of arrangement, one can avoid current contribution from convection. So that whatever the current you measure would be a pure representation arises from diffusion alone. Now, the moment you talk of diffusion, there are two different laws which governs the diffusion process. They are called Fick's first law and the second law. The first law talks about flux of the species is directly proportional to the concentration gradient. What do I mean by flux, which is designated here as J, which could be equivalent to I by NF. Okay, I by NF. The proportionality constant is nothing but your diffusion coefficient. And if you move that NF from the left hand side to the right hand side, you would end up with the equation where current I is equal to NF D dou pi by dou x. That is nothing but your concentration gradient. What do I mean by concentration gradient? The number of molecules of the redox species present at the interface to the number of molecules present in the bulk. This ratio would give you the concentration gradient. So the Fick's first law talks about the resultant current is directly proportional to the concentration gradient, and it is also directly proportional to the diffusion coefficient. Do you get me? That's the Fick's first law. The second law talks about not only with respect to distance away from the electrode, meaning that x in the equation represents the distance away from the electrode. Okay. So not only with respect to concentration gradient, how the current changes with respect to time as well. So, or how the concentration profile changes with respect to time. That kind of information is provided by Fick's second law. So these are the two laws that directly correlates with the electrochemical process. In fact, I would stress upon again that all the electrochemical concepts and all the electrochemical equations are derived based on the assumption that diffusion is the predominant mode of mass transfer, and these two laws like Fick's first law and Fick's second law of diffusion uh, deals about the diffusion associated with the redox process. Now, let me get slowly into the techniques now. These are some of the fundamental concepts one would be interested to understand the electrochemistry as a whole. Now, you guys would have heard about this Nernst equation. This is the equation which describes the system at equilibrium. Okay, the system at steady state. I mentioned why equilibrium is important, because at equilibrium alone, the electrode-electrolyte interface exhibits its real characteristic. I rephrase my sentence. One can determine many kinetic parameters like electron transfer rate constant, diffusion coefficient. In terms of electrocatalysis, many catalytic parameters, kinetic parameter one can determine at equilibrium that will provide information and real characteristic of the material you use for such application. Okay, and Nernst equation describes the system at equilibrium. This forms the basis for potentiometry technique. Okay. Now, apart from this, this is the equation. If you are doing a PhD in electrochemistry, I would recommend that one should know this equation. This is called the Butler-Ulmer equation. This equation provides a relationship between current and potential under all given conditions. Okay, so this equation provides information about relationship between current and potential under all given conditions. This is called Butler-Ulmer equation. For example, what's the relationship between current and potential at equilibrium? One can determine parameters like charge transfer resistance, exchange current density, etc. And you can apply a small perturbation. Okay, recall I was hitting a person and that person is hitting me back. Instead of hitting him, you can simply tap him, just like a tap. Minimal perturbation, so that how the interface behaves. That relation is also provided by this Butler-Ulmer. That's a kind of Tafel equation one would get for a minimal perturbation. Eta is equal to A plus B log I, where A and B are nothing but Tafel slopes. This equation is very much essential when you talk about this water splitting reaction. I will talk about this tomorrow again. So the Tafel slope value provides information about what is the mechanism behind such water splitting reaction. Okay, what is the mechanism behind typically hydrogen evolution reaction, and that kind of information one would get from Tafel relation. So, like this, under equilibrium, under minimal perturbation, and far away from equilibrium, all these information one can get from this Butler-Ulmer equation, and one can get the relationship between current and potential through that equation. Now, we do have techniques in electrochemistry that describes the system at equilibrium, provides a relationship between current and potential at equilibrium, near to equilibrium, and far away from equilibrium. For example, the techniques like potentiometry. Okay, I'll talk about potentiometry in a while now. The techniques like potentiometry, open circuit potential measurement, or OCV, OCP some people call, open circuit voltage, open circuit potential, equilibrium potential, E0 value, all such kind of measurement at equilibrium provides information about the structure of the interface. Okay, so those techniques come under equilibrium technique. And near to equilibrium, near electrochemical impedance spectroscopy comes under that category. And the final one, which is far away from equilibrium, like in terms of controlling the mass transfer, controlling the diffusion process, etc. Techniques like voltammetry, linear phase voltammetry, cyclic voltammetry, pulse voltammetry, those techniques come under that category. So that one can able to understand the electrode-electrolyte interface through many different techniques, so that it provides information about the relationship between current and potential and can correlate such phenomena to the interface. Okay, so that's the whole idea behind using electrochemical techniques. If we use a constant current based method, those techniques are called galvanostatic. One can also use constant potential, those techniques are called potentiostatic. One can vary the input signal with respect to time duration. Those techniques are either potentiodynamic or galvanodynamic measurement. One can use both AC and DC signals as a perturbation, so that you can categorize these techniques into AC and DC different techniques. In all these techniques, what you do is you either apply a potential or current at fixed time or at fixed duration, or one can vary the potential or current perturbation by varying with respect to time, like pulses. In all these techniques, one can measure the changes in current value or the potential vice versa and correlate with the concentration, etc. The beauty of electrochemistry is not only these fundamental concepts, you can also couple the electrochemical technique with other techniques like EPR, for example, or NMR or EPR, for example, so that you can carry out a spectroelectrochemical technique, or one can use a hyphenate technique like scanning electrochemical microscopy, etc., so that you can image the surface of the electrode as a whole. All these techniques one can do with the electrochemistry. So, how are we coping up with the time, sir? How long can I talk?
Maybe now the time is almost 1:30, sir. How many more slides do you have for this particular lecture?
I do have many slides because I thought of covering whole technique, but it doesn't matter since tomorrow also I have time. I can adjust.
Now the time is too late because they all have to go for lunch, because morning 9:30 was started today.
Okay.
Okay, so maybe we can continue in another 5 minutes and we can continue for the next session tomorrow.
Sure, sir. Yes, I understand. So maybe what I will do is I will highlight maybe a couple of techniques in 5 minutes.
Yeah.
And probably tomorrow I can continue this and correlate with the electrocatalysis process.
Yeah,
Is it okay?
Yeah, it's fine, sir. Thank you.
Yeah. Okay. Sure. Okay. Now, probably for the next 5 minutes or so, let me talk about this potentiometry and amperometry, and other techniques we will talk tomorrow. Okay. So, potentiometry is a technique in which you measure the potential at zero current. Delta I is zero. Okay. So, you measure the potential with respect to change in time or change in concentration of the analyte. In fact, this technique comes under equilibrium technique. All the ion selective electrodes, including pH electrodes or ion selective electrodes specifically for chloride or Na+, K+, etc. All these electrodes work based on the principle of potentiometry. And Nernst equation governs the basic principle behind potentiometry, so that whatever the potential you measure could be directly correlated with the equilibrium constant. So this technique is a very, very powerful technique. The other kind of technique is amperometry, where at a fixed potential you measure the change in current with respect to time or concentration. Okay, at fixed potential you measure the change in current with respect to either time or concentration of the analyte. So that technique is called amperometry. In fact, the Cottrell equation provides information about the amperometry, measure the current and correlate with the parameters like diffusion coefficient, concentration of the species, etc. I is inversely proportional to the square root of time. That's the key point behind the amperometry. In fact, one can distinguish the Faradaic and non-Faradaic process using this technique. If you look at the output in amperometry, there would be an initial sharp drop in the current value, and after that it will attain a steady state. The initial sharp drop talks about the double layer charging current, and the steady state current would give you information about the Faradaic process. Okay, do you guys get me? The initial sharp drop in the current, which is of the order of 1 power 1 by 6, okay, which is very fast. That correlates with the non-Faraday, and the steady state measured current would provides information about the electron transfer, Faraday process. Okay. Now, instead of fixed potential, one can apply a potential pulse. Okay. The width of the pulse talks about time duration, and the height of the pulse talks about potential difference. Do you get me? In case of pulse technique, you can change the way in which you apply a potential with respect to time as a pulse. So the width of the pulse talks about time duration applied to perturb the interface, and the height of the pulse talks about potential values, so that by applying such kind of pulse technique, such kind of chrono techniques, what do I mean by chrono? With respect to changing time, you can vary the input perturbation signal. So such kind of chrono techniques one can apply to monitor the change in current. So predominantly, all the most of the sensors which are available in the market, for example, glucometer, okay, all these kind of sensors works based on the principle of amperometry based technique. So these two techniques are very powerful in electrochemistry. So what I will do is tomorrow I will maybe talk about and highlight in a very crisp manner some of the basic concepts behind voltammetry, impedance spectroscopy, and then I will talk about directly electrocatalysis and water splitting reaction. Okay. So to conclude as of today, I would say that electrochemistry, it's not just about current or potential, or measuring any electron transfer rate constant or electron transfer reaction, etc. It could be directly used to solve the global issues. Maybe I will try to highlight tomorrow why one has to involve in doing research, why one has to worry about taking research as a career. So electrochemistry could be used as a very simple but yet powerful tool to solve global issues and provide solutions to issues what we face during our day-to-day life. Okay, so probably with that I will stop
Yes,
for
sir.
today, and I will conclude maybe today. So I would again thank for the opportunity, and I would be happy to answer any queries or questions you guys may have. Thank you for your patience listening.
Thank you. Thank you for your nice presentation, sir. Maybe one or two questions from the participants, because the time is too late for lunch. So maybe